Welcome back to Topic 4 Applications of Derivatives. This is our second to last lesson in AP Calculus AB for Semester 1, and really this is going to conclude your derivatives unit, this differential calculus, calculus of derivatives, and then next semester we'll move into integral calculus, calculus with integrals. Next semester we'll still use derivatives, of course, often, but it's more everything we've done this semester just applied to next semester, so no new rules, which is kind of fun. This is your second of really 3 days on particle motion. Yesterday was a pretty huge information dump where you got all sorts of relationships, and in fact I'm going to rewrite this quickly. We learned that position is our top equation if we're envisioning like a ladder, and then if you take the derivative with respect to t, it brings you to velocity. And then if you take the derivative of that with respect to t, it brings you to acceleration. We also learned a bit about units, right? Where we learned, let's say that the units of position was, let's say, miles. And if we take the derivative with respect to time, let's say it's hours, we get something familiar. Then velocity has units of miles per hour. Then acceleration is miles per hour, or miles per hour squared, if you would like. We concluded last class with 2 practice problems. One problem used a table and one problem used a graph, and for both of those with the graph and the table of velocity. Now, in calculus, we've mentioned this a few times, we'd really like to try and gnaw on specific topics, and so we're going to try and gnaw on particle motion. What that gnaw means, we're going to look at it from a graphical perspective, did a bit of that last class, a numerical perspective, and numerical is essentially a list of numbers, aka a table. We did that last class as well. The A can either stand for analytically or algebraically. I think of it as algebraically. And generally that means you have an equation that you're doing some algebra with, and that's what we're going to focus on to start with today. The W is a written, where you get a written scenario, and you have to apply calculus to it. So here we go. A particle moves along the x-axis so that at time t, its position is given by that equation there. Very exciting. And then you have a bunch of questions here. So why don't you go ahead, take a few minutes, take your notes out from last class, and see what you can do with this. And then at the end, we will go ahead and go over it and see how you're feeling. Ready, set, go. All right. Let's begin. At time t equals 0 is the particle moving left or right. Well, the equation that controls the direction a particle moves is the velocity. We're given position, so that I think means we need to find velocity. And I always set this up by showing that we're going to take the derivative of x, then stating that that derivative is the velocity, and then finding the velocity, right? 3t squared minus 12t plus 9. And since I've mentioned this before, if we're going to be working with this, we should probably factor this equation. We might need this later on. So let's factor out a 3. Becomes t squared minus 4t plus 3. And I think we can factor even further to t minus 3 times t minus 1. All of those are satisfactory velocity equations. Let's see what the heck they're asking. At a time t equals 0, is the particle moving left or right? Well, we just need to find the velocity value at 0, and I think that'll tell us. So v of 0 equals, I'll use my factored form. Maybe it's, well, actually, no, I'm lying. I'll use this form right here. That's way easier, because with this form, everything here becomes 0, and it just leaves you with positive 9. Now, notice I didn't show substituting in 0 here, because the AP exam doesn't care how you get to the answer. They want to see what are you trying to do, and what is your answer. The work in between is all algebra. The setup and the answer shows a knowledge of calculus, and that's what they're testing you. So we can just state v of 0 equals 9. If you really felt like it, you could substitute 0 in here, and you could show this extra work, and very exciting, you still get 9, but you don't have to, and you might as well save time. So v of 0 equals 9. What's our conclusion? Well, as v of 0 is greater than 0, as the answer to v of 0 is positive, the particle is moving. Which way does a particle move if velocity is positive? Oh, that's right. If we think of an x-axis, the positive numbers are to the right, so we are moving right. Very nice. B, at t equals 1, is the velocity of the particle increasing or decreasing? Ho ho! They are asking us where a function is increasing or decreasing, and to determine where a function is increasing or decreasing, you always take the derivative of that function. So if we want to check the velocity here, we're going to need to start with our x prime of t up here, and I need to take the derivative of that. It's your choice on how you want to show it. You could show a bunch of it. The second derivative of x is the first derivative of v, which is the acceleration, and the derivative of that guy is 6t minus 12, or 6 times t minus 2. At t equals 1, is the velocity increasing or decreasing? Well, we should probably just find, and I'm going to use v prime, because they're not really asking about acceleration here. I mean, they are, but if you're asking increasing, decreasing, really they're just asking about the derivative of the function, so I'm just going to keep v prime. You'd get credit for any of those, though, not a big deal. V prime of 1, well, hopefully we can do some mental math. 6 minus 12 gets us negative 6. And a conclusion. As v prime of 1 is less than 0, the velocity is decreasing. Easy enough. All right, part C. Find all values of t for which the particle is moving left. Well, if we're going to find all values of t, what they really mean are the intervals where the particle is moving left. And whenever we find intervals, we set up a sign chart so we can see those intervals. The first thing we'll have to do is figure out when is the particle not moving? When does the particle have a velocity of 0 so we can subdivide our sign chart? So let's go ahead and show that we're setting velocity. I'll switch back to my soothing green from above. We need to set velocity equal to 0. Looking up above, we have a bunch of velocity equations. I'm going to use the factored one over here. So we are setting 3 times t minus 3 times t minus 1 equal to 0. And I bet we can see that our time values are 3 and 1. So what did we find? We found the times at which the particle is not moving. So we've clearly not answered the question yet. Let's build ourselves a friendly little sign chart. What do we know about this? They didn't tell us anything about time. They didn't give us an interval. So you can say negative infinity to infinity. Realistically, a real AP problem would tell you that the time values are greater than 0 or equal to 0, but we'll go the whole interval. Why not? Right? So we have 1 and 3. We're looking at the sign of velocity to determine the direction. We know these values, these are critical points, made velocity 0. And so now we just try various numbers. And actually, if you had set this equal to 0, you might have made your life a little bit more complicated, because by setting this to be negative infinity, we can see that we're allowed to plug in 0 because 0 is on this interval. If you had set this equal to 0, you would have had to use a fraction to substitute in. So it doesn't really matter. You'll get the same answer. Let's go ahead and try 0 in here. If you substitute in 0, I think we'll get, you can picture that, we'll get a negative times a negative, which is a positive. If we substitute in 2 on our next interval, we get a negative and a positive, which is a negative. And then if we substitute something greater than 3, like 4, we will get a positive. All right. Well, now we can take a look at this. And again, I tend to draw arrows here. Positive velocity, negative velocity, positive velocity. To answer the question, find all values of t for which the particle is moving left, we would say something like this. The particle is moving left on 1 to 3. And as a reminder, it doesn't matter if you're open or closed here. They do not care about your interval. I tend to do closed, but you could use open. You'll be fine. It's moving left on that interval because v of t, well, what was the giveaway? I think v of t was negative there, right? Because v of t is negative. And we're set. Last one. Find the maximum acceleration of the particle on the interval 0 to 5. Ooh, this is optimization. We're trying to determine when is the acceleration at a maximum. So we already have the formula for acceleration. I think that's this guy right here, isn't it? So we know that acceleration is 6t minus 12, or we did factor it to 6 times t minus 2. Great, but if I want to determine where that equation is at a maximum, then yes, it's the candidate's test, but the way the candidate's test works is take the derivative of that equation to find its critical points. So although we don't have a meaning for the derivative of acceleration, it is called the jerk for you physics folks, and I'm not being rude, it is literally called jerk, J-E-R-K, and you can look it up if you'd like. We don't deal with that in calculus. All we're going to do, though, is whenever you want to maximize or minimize an equation, take the derivative. So I'm going to take the derivative, which is just 6. We're going to try setting the derivative equal to 0, but there are no values that can turn 6 into 0. It's just 6, so that doesn't happen. There are no critical points here, which means we're just going to quickly build a candidate's test where we need to test time values in acceleration, what time values? Well, normally we'd include critical points, but there aren't any. So instead, just the endpoints, 0 and 5, aren't they? Okay, and let's plug these endpoints in. So if I wanted to find a of 0, that is just 6 times 0 minus 12, which is negative 12. If I wanted to find a of 5, that becomes 30 minus 12, which is 18. Out of these two, which one is largest? That one is, right? This is the maximum acceleration. That's our candidates test. Normally we'd substitute in a critical point. There are no critical points, and that's that. Now, the title of today's lesson is Speed and Particle Motion. And we did have a brief discussion about speed yesterday, right? Just a quick reminder, we said if we have velocity, and if we had an example velocity like 3 miles per hour, make it negative 3, I guess, that velocity is what's known as a vector, and it tells us two components. It tells us first the actual speed. The speed is 3 miles an hour, but which direction? Oh yeah, this sign tells us we're moving to the left at 3 miles an hour. Now we're going to expand on that for today. Speed tells you how fast something is moving without regard to the direction of movement. So you're basically saying, yeah, I know that there's going to be a sign and a value. Speed is, though, just the value. Who cares about the sign? So let's take a look at a quick example. Given below is a table of velocities for a particle moving continuously at specific times. A and B. What is the minimum number of times the particle is at rest? Well, at rest, as a reminder, is when v of t equals 0. So where is v of t 0 on here? Oh, nowhere. Well, that's a bummer. Well, how can we do this then? Oh, wait, this is moving continuously. You're starting at negative 4, and you need to get over to 2. So if you picture a graph, and we have negative 4 down here and 2 up here, and you're starting down here, and eventually you have to get up to 2, will you eventually have to cross over where y is 0? Certainly. Right? There's no other way to do it because our graph is continuous. So I'm pretty sure that our particle comes to rest somewhere between a time of 0 and 1. What about the rest? Is 0 guaranteed from 2 to 4? No. 4 to 12? No. 12 to 36? No. I think we can at least guarantee, though, that this will happen at least once. So the minimum number of times the particle is at rest, we would say 1 time, because v of 0 is less than 0, right? Negative 4 is less than 0, which is less than v of 2, right? That's 2. I'm sorry, not v of 2. v of 1 is 2. And as v of t is continuous, do we see where we're going yet? On 0, it should be t, 0 to 4, closed interval, then the IVT guarantees some time v of t equal to 0. That IVT always rearing its friendly little head saying, hey guys, I can prove something's happening even if we don't know where. And that's that. I don't know. You probably even could have said from 0 to 1. 0 to 4 is a little bit extra, but it doesn't matter. You get the same points. All right, part B. What is the minimum number of times the particle is moving at 4 meters per second? Well, 4 meters per second. Well, we know it's moving at 4 meters per second, definitely at t equals 2. Anywhere else? And if you try to use the IVT, you're like, well, 4 isn't between here, isn't between here, it is 4, not between there, not between there. It seems like there might only be one spot. But then hopefully you're saying, whoa, whoa, whoa. Isn't the particle moving at 4 meters per second at a time of 0 as well? And you're right. Because although this says negative 4, that just means moving left at 4 meters per second. And so when we're looking for speed, we need to be very careful. We need to find all the negative and positive values where that speed occurs. And that gets a little tricky. And in fact, I think this next example might do a good job highlighting it. Given the equation for a particle's velocity, blah, 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 where t is the time in seconds and v of t is the meters per second, at what time or times does the particle have a speed of 8 meters per second? Well, it might seem somewhat obvious, or, it might make sense that we should probably figure out where v of t is equal to 8. So we set t squared minus 6t equal to 8. Okay, and then we go here, 6t squared minus 6t minus 8 equals to 0. And then you're going to look at this and go, ooh, we want to try and factor this guy, huh? Well, but then you're going to try and factor it, and you actually might be able to. I'd be very impressed, but you might be able to factor it. I think, though, you're not going to find anything that multiplies to make 8 and adds to make negative 6. Those negatives are definitely a big issue here. And so you might have to turn to the quadratic formula, which is a real bummer, but it's doable, right? Just a quick reminder of that quadratic formula, negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And then you simplify down, so 6 plus minus the square root of, what is this, 36 plus 32 over 2. I guess just to say t equals, huh? So we're solving. And so last but not least, 32 and 36 looks like it's going to be 68, all of this over 2. And so we found 2 time values. Very exciting for us. 2 things to remember. First, you don't actually need to know the quadratic formula for the AP exam, which seems like blasphemy. But yeah, there's never, ever, ever going to be a problem where you have to use the quadratic formula. So should you know it? Yeah, and actually that's why I like doing this one, just because it reminds you of how to solve an equation you might not know how to factor. So is that it? Those are the only 2 time values? Well, no. These are the 2 time values that causes your velocity to move to the right, or your particle to move to the right at a speed of 8. But what about all the times that cause your particle to move to the left at a speed of 8? And so we also need to set v of t equal to negative 8. And so what does this look like? T squared minus 6t equal to negative 8. Add the 8 over so we can use that zero product property. I know I put an extra plus there. That was awkward. There we go. And actually, you'll find this one factors really nicely, doesn't it? Look at that. And we get 2 more time values. And these are the times where the particle is moving left, but still at a speed of negative 8. And so the question you might be asking here is, well, every time they ask for speed, do I have to set up 2 separate equations and solve each one separately to figure it out? And the answer is, yeah. Now, is there a faster way? Also, yeah. But at its core, this is what we're doing. How often does this come up? Maybe once on the AP test. Maybe. Speed is not that often asked about, but it does happen. All right, so I promised you maybe a faster way, so we're going to have a brief interlude here. The interlude is, how does absolute value affect numbers, and why? Well, hopefully you remember that absolute value essentially measures how far away a number is from 0. And so if we wanted to measure how far away 6 is from 0, then the answer would be 6. But if we wanted to measure how far away negative 6 is from 0, the answer would also be 6. So we say that absolute value has the property where it makes a value positive, right? Both of these become positive 6. So if we wanted to solve the absolute value of x equals 6, what do we actually do? Well, we make 2 equations, where one equation is x equals 6, and the other equation is x equals negative 6, right? We make 2 equations, one positive, one negative. Or if you wanted to go backwards, if x had been set equal to 6 or negative 6, couldn't we combine both of those into one nice cute little equation, the absolute value of x equals 6? Maybe you see where we're going, right? We set one equation and the other to 2 different values, one positive, one negative. There might be a faster way. Well, we have 2 more things to look at. How does applying absolute value to a function affect the function's graph? Well, if the absolute value is going to make every answer positive, every output positive, and the output of a graph is the y-axis, then wouldn't it change all of our y values to positive values? So for example, here I have this original graph. Hand slip there, sorry. I have this original graph of y equals the absolute value of f of x. But they asked us to superimpose, place on top of, the graph of y equals the absolute value of this. Well, let's look at the right side first. All of the y values over here, all of the outputs are already positive. So this graph is going to look exactly the same. But on the left side, these have negative y values, so when you apply absolute value, that shape is going to flip upwards and look like so. Okay, let's put all this together. You ready? This is calculator active. I hope you have a calculator in front of you. If you don't, pause it and go grab one. And although you can do this on Desmos, you need to get into the habit of using a graphing calculator because you can't use Desmos on tests, especially the AP exam. So find all places where the speed of the particle is 2, given the position function of the particle is x of t equals secant of t, and only looking on the time interval from negative pi over 2 to pi over 2. All right, 2 ways to do this. The way we shouldn't do it and the way we should. The way we shouldn't do it. We have this secant. We know we want speed, which means we need velocity. So x of t is secant of t. The velocity is found by taking the derivative of position, and we all remember the derivative of secant, right? It becomes secant of what's inside times tangent of what's inside. Then what? Well, this part is important, even though I'm telling you that this isn't the way I would suggest you do it. If we're looking to see where the speed is 2, then we need to do 2 things. We need to set the velocity equal to positive 2, and we also need to set the velocity equal to negative 2. We need to find where the particle is moving to the right at a speed of 2, and where the particle is moving to the left at a speed of 2. But couldn't we combine that together? Couldn't we say that really we just want to solve the absolute value of v of t equals 2? Don't those say the same thing? Now, keep that in mind. I'm going to erase it and rewrite it over here. So we do need to solve that. However, if you were trying to solve this by hand, it's pretty tricky to solve absolute value equations by hand, so you might just want to stick to it like so. We'd say secant of t, tangent of t equals 2, or secant of t, tangent of t equals negative 2. And then I'd say, cool, solve each of those. And then you would probably say, how? And then my answer would be, I don't really know. That's a great question. So this is calculator active for a reason. Whenever you get to an equation that just seems extreme in terms of solving, it's probably a calculator active problem, and they expect you to use the calculator to do the dirty work. So how do we solve this? Well, we do need to solve this equation. So if you didn't do any of this, it's okay to keep it here. If you didn't do any of that, you would still need to state this, because this right here is telling you what you are looking for. This is your setup. You're trying to figure out where the absolute value of v of t equals 2. And if you didn't want to do that, you could have also stated, you could have also stated this. But because this is calculator active, there's very little work we need to show. So what I'm going to do here is I'm going to say the absolute value of v of t equals 2, and then I'm going to go straight to the answer and say, here are the answers. They're not going to question how you found them. They need to see the setup and the answer. The how you found has nothing to do with calculus. The how you found in this case has to do with your calculator. So let's begin. We have x of t equals secant of t. I'm going to pull up my calculator, and I very cleverly already have secant of x in this case ready. I always use x here, and you'll notice if you look at up here, I always forget that my calculator does not like my pen. There we go. We have to use x because it says a function of x, so we do need to use x as our variable. Cool, but I don't actually want to graph secant of x. I want to look at the velocity, which is the derivative of secant of x. So I'm actually going to go ahead and turn this guy off, right, hitting that little check mark, and then let's go down to, no, I said off, thank you, and then let's go down to the next line. Remember how to do this? Remember how to graph the derivative? We use the quick key next to the 9, this guy over here, and then we choose the derivative button. Okay. If you're on the 84, you're in the y equals, and you just do math, and then 8, which is n derivative. And then we're going to do d dx of what? Well, that's easy. The of what here is f1 of x. So f, good, 1 of x. Cool. Graph the derivative of whatever is in f1 of x. Enter, and there's my derivative. Looks intimidating, but also kind of cool, right? You can see the, I don't know, the glasses, and they're either up or down or something like that. It's like one of those where you see faces, depending on how you look at it. It's not, but it could be. We also need to remember, though, they gave us an interval. They said only look between negative pi over 2 and pi over 2. So menu, and then window zoom, window settings. We're just going to go on the x's from negative, and I'm always too lazy to hit the pi button, so negative, of course now I can't even find the letter p, pi over 2, then tab to get down to pi over 2. Enter, and that's much nicer. I love that. Great. Now, we don't just want to set or solve, or maybe we should actually talk about why I'm graphing this first. We're trying to solve the absolute value of v of t equals 2. And remember, whenever you have an equation that you don't want to solve algebraically and you have two separate sides, what we can do is kind of turn this into a system of equations, and you wouldn't show this part, but what we're doing is we're really going to graph the first system, y equals 2, and then we're also going to graph y equals the absolute value of v of t. And what we do is, you might remember when you solve a system of equations by graphing, you look for their intersection point. Okay, so if I jump back here, I'm going to need to go back up one more time. Okay, second try. And I'm going to need to graph the line 2. That's not what I said to do. Second try. Graph the line 2. There we go. Now, you can tell that this line intersects my derivative in one spot, but there is a slight issue. Because I don't want to solve where 2 equals the derivative. I want to solve where 2 equals the absolute value of the derivative. But that's easily done. I'm going to hit tab, go back up. There's a few ways to do this. Maybe we'll go the long way around. I'm going to turn this guy off. You could have included the absolute value here if you were more on top of it, but I was not. And so I'm going to get the absolute value. The absolute value is actually labeled on the quick key button. You can see it down there. So I'm going to do absolute value. Where is that guy? Oh, it's on the upper right, isn't it, over here? The absolute value of, well, I think my derivative function was in f2 of x this time. f2 of x. There we go. And it doesn't shock you what it looks like, right? The original graph kind of looked like an S. When you applied the absolute value, it just flipped up the other side. How do we solve this? Well, solving a system involves finding where the two functions intersect, and I see 2 intersection points. My guess is based on symmetry. They're the same intersection point, one positive, one negative. Never hurts to check, but I'm telling you they are. So we're going to do menu, analyze graph, and this time we're doing the intersection, so 4. Okay, and I want to find here and here. There we go, but I never trust that 0.896. I want to see if there are any more decimals. There are 0.8959. 0.8959, and really it was plus minus, so you could find the other one, but I'm telling you right now it's the exact same, it's just the negative value. And so we have solved, or we have found the times that generate a speed of 2. Now, if you didn't remember the absolute value part, could you have still done this problem? Certainly, right? You could have done this problem, and I'm going to show you one more way to do it by getting rid of this guy, shoe, and turning back on f2 of x, hitting enter. I said enter, but over here. There we go. Now, you'll notice that they only intersect in one spot. So you're only going to find that positive value. How do you find the negative? Well, you do kind of the opposite of what we just did. We have the line 2. Let's also graph the line negative 2, right? So if I graph this line negative 2, it's f10 of x, whatever, you will see that the line intersects down here. And so this will show you the 2 intersection points, one where the particle is moving to the right, velocity of positive 2, one where the particle is moving to the left, velocity of negative 2. So the easiest way to solve one of these absolute value, or one of these speed equations to me, is set up the absolute value of velocity, but there are other ways to do it. Last part of today. This part's quick. We have talked about what causes velocity to increase or decrease, but that's actually a pretty confusing concept, because if velocity is increasing, it is possible for your speed to still be decreasing. And we're going to take a peek at this right now. So what I think of is if you have a positive velocity, that means you're moving to the right. But if you have a negative acceleration, I think of somebody who's like standing here and they're like trying to hold on to you and they're trying to like pull you backwards. So you're still able to move to the right, but because they're pulling you backwards, you'd be slowing down. And that's kind of weird, this positive velocity but negative acceleration. And there's a whole bunch of combinations that either result in you speeding up or slowing down. And so what we're going to try to do on this last section is determine when is your speed increasing versus when is your speed decreasing. That is slightly different than increasing, decreasing velocity, as we're about to see. Now, I've given you 4 situations, and the situations are all fairly similar. This is the graph of velocity every time. So you can label your y-axis as velocity if you'd like. In this graph, each horizontal grid mark represents 1 unit of time, and the vertical represents 4. You don't really need to know that, though. For each situation, fill in the speed at each time, then answer the questions based on the graph. So I'm going to do 1 and then have you guys try 3 more. They go pretty quickly. At a time of 1, the velocity is 1. This is 1, 1. What is the speed? Well, the velocity incorporates the speed. The velocity of 1 means we're moving to the right at a speed of 1. Same thing, speed of 2, speed of 4, speed of 8, speed of 16. In this situation, the velocities are all positive values. We know they're positive because look, they're positive values. And are the velocities getting bigger or are they getting smaller? Well, they're getting bigger, right? If you look at the graph, it has a positive slope, so the velocity is increasing. Because the velocity is increasing, we know acceleration, remember increasing velocity, positive slope, slope of velocity is acceleration, so we know acceleration is also positive. Lastly, by examining the table of values, we can conclude that speed is, well, what's happening to the speed? I'm pretty sure the speed is getting larger as well, so the speed is also increasing. No shocks there. Now, why don't you guys try the other 3 and then come back and see how you did, and we'll finish this off. All right, you're back. Let's fill this in quickly. So, second situation. The velocity is negative, and because the graph is going down, we know the velocity is decreasing. Because the velocity is decreasing, and that's the derivative of velocity, then we know acceleration is negative. Let's get these speeds in here. -1 for a velocity means moving left at a speed of +1. Speed of 2, speed of 4, speed of 8, speed of 16. By examining this pattern, can't we determine that the speed is increasing? And that's interesting. Everything else here was negative, but the speed was increasing. Versus up above, everything was positive, and the speed was increasing. 2 more. Speed, easy enough, just the absolute value of velocity here. In this situation, the velocity is clearly negative, right? Negative values below the x-axis, 2 ways to think about it. And if you think about the slope, then the velocity is increasing. Because velocity is increasing and acceleration is the derivative of velocity, acceleration is positive. And by looking at the table of values, what's happening to your speed? Well, your speed is getting smaller. Your speed is decreasing. Last but not least. In this situation, the velocity is positive. Look at those positive values above the x-axis, and the velocity is decreasing, negative slope, right? Because velocity is decreasing, acceleration is negative. Looking at this table of values over here, because our speeds are getting smaller, speed is decreasing. So in which situations was the speed increasing? Those are situations 1 and 2. When the speed is increasing, what do we know about the signs of velocity and acceleration? Well, looking up here, see this velocity was positive and acceleration was positive for increasing speed. Okay, down here, velocity is negative and acceleration is negative, and that also resulted in increasing speed. And so I think we might be able to conclude then that when speed is increasing, the velocity and acceleration have to have the same signs. And this to me makes logical sense. Because if your velocity is positive, that means you're moving right. If your acceleration is positive, that means that you are pushing to the right, right? You're accelerating to the right and moving to the right. It should make sense you're speeding up. And then in this other situation, if velocity is negative, you're moving to the left. And if acceleration is negative, that means you're accelerating to the left. So if both your signs are the same, it means they're acting in the same direction, and so you should be speeding up either forwards or backwards. finishing this off. Which situations was the speed decreasing? Well, that's going to be 3 and 4. I bet you can already guess this one, but let's take a look. The velocity here was negative, but the acceleration was positive, and that resulted in decreasing. However, here, the velocity is positive, and the acceleration is negative, and that still resulted in decreasing. When speed is decreasing, velocity and acceleration have opposite signs. Also, just based on the relationship of velocity and speed in all of these, speed always became positive regardless of what velocity is. So it's very commonly said that speed is the absolute value of velocity. All right, let's summarize. If velocity and acceleration have the same sign, they're either both negative or both positive, speed then is increasing. You are speeding up. If velocity and acceleration are opposite in sign, then your speed is decreasing. Last but not least, looking at the graph of velocity, and this is seldom said, but I think it's a nice way to justify to yourself. Speed is decreasing when the graph does what? Well, these are the two situations where speed's decreasing. And notice as you move to the right, isn't the graph getting closer to the x-axis? And so that's true, that speed decreases as the graph approaches the x-axis. However, on the two situations where speed was increasing, the graph is veering away from the x-axis. And that makes sense because essentially these are all graphs of velocity. And if your velocity approaches 0, that must mean that your speed values are also approaching 0. You're slowing down. However, when the graph goes away from the axis, speed is increasing because now your velocity is either going very negative, so very to the left quickly, or very positive, very to the right quickly. Now, that's all we have for today. It's a pretty quick lesson. I wanted to give you time to get started on your independent practice. As a reminder, your independent practice from yesterday, day 50, and today, day 51, are the same, and I actually suggested you probably don't start it today, or didn't start it yesterday. You should do it today, though. So go ahead, tackle your independent practice. I think you'll find it's not too terrible. As always, the solutions are posted. Thank you for hanging in there. We have one more day, and it's a little bit more about particle motion.